welcome to our presentation tonight with the monthly Watershed Education Series. My name is Patty Levine, and I'm a member of the Watershed Education Committee. We've been putting on these seminars or these classes for about 7 years now. Tonight's presenter is originally from the San Francisco Bay Area. She is an associate professor at SUNY Geneseo. Her research centers around the physiology and ecology of deep sea animals, including the planet's deepest living fishes. Her speaker completed her undergraduate degree at Whitman College in Walla Walla, Washington, then her PhD in marine biology from the University of Hawaii in 2017, before working as a postdoctoral researcher at Friday Harbor Labs at the University of Washington. Documentary by NHK, a Japanese broadcasting company. At SUNY Geneseo, she teaches animal physiology, marine biology, science communication, and works with a fantastic team of undergrad researchers to understand marine organisms and their adaptation to the deep seas. So without further ado, let's learn more about these fascinating creatures and much more. I give you Dr. Mackenzie Gerringer.
Thank you so much. Thank you. And thank you for being here, for braving the cold in person, for joining us on Zoom. We're very excited about this opportunity to talk about one of my favorite habitats. I love questions, so feel free to share questions. We can have a dialogue about some of the things that we're looking at. And you may or may not think about the deep sea very often. Maybe after tonight you will a little bit more. But the deep oceans are actually the largest habitat on our planet. So most of the places that organisms can live are in the deep ocean. About 70% of where organisms can live is deep sea. But the deep sea remains, as many of us know, some of the least explored habitat on Earth. And there's a lot of opportunity for discovery in these really amazing habitats. And so this is the part of the science talk where I would show you some beautiful imagery of the habitat that we're going to look at today. So here is my beautiful imagery of the habitat we're going to look at today. The deep sea is dark. We have brought some cameras into this environment so I can show you some better images today. And from a human perspective, we often think about the deep sea as being quite harsh. So there's no sunlight past about 3,000 feet. It gets very dim even before that. It's cold temperatures, colder outside, but it's close to the temperature of our refrigerator, about 33 to 39 degrees Fahrenheit. And there's limited food availability. So a lot of the deep ocean, most of the deep ocean actually relies on stuff at the surface to sink down to be able to feed it. And there's really high pressures in the deep sea, up to 1,100 times what we experience at atmospheric pressure. And that's the equivalent of about an elephant standing on top of your thumb at those deepest ocean sites. So some really incredible adaptations for those conditions. But yet, the deep sea is home to many extraordinary organisms. So even though we think of this habitat as being difficult to live in, or extreme, or harsh, or otherworldly, for many beautiful organisms with whom we share our planet, this is home. And I'll share a couple examples today. I'll just point out a few favorites. This is a frogfish that is mostly good at walking and very bad at swimming. It hangs out on the seafloor and it actually waits for prey to come to it. The Dumbo octopus here is a favorite as well, or sometimes called the flapjack octopus. An amazing organism that's living down at these deep depths. And then this one is actually a sea cucumber that's able to swim. And I think of it like a beautiful ballerina. It also went viral on the internet as a headless chicken monster. So you can choose what you want to call it. These really amazing habitats. And in my lab, we're interested in what it takes to survive and thrive in these deep sea habitats. But it's important for us to keep in mind that the deep ocean is not just one soup. It's actually many habitats that are each have their own communities. They each have their own set of characteristics. And so if I asked you to close your eyes or look down and picture the deep sea, what might you picture? So if you've got your eyes closed, you're doing well, it's dark, but what types of organisms might live there? Maybe you're picturing a sperm whale and a giant squid battling it out. A lot of these images that come from, or that we think of when we first think of the deep ocean, come from what we call the twilight zone, or we call it the mesopelagic. This is the spot in the deep ocean about 3,000 feet down where it's getting dim and dark, and a lot of organisms have to be adapted to that environment where there's nowhere to hide, there's not very much food, and we end up with some really extreme and incredible adaptations to this. So one example is the fangtooth, whose teeth are so large it actually has to have specialized grooves to be able to shut its mouth. Or fish like the viperfish that cannot shut its mouth with its teeth in it at all. And fish like the anglerfish that you may know from the film Finding Nemo, or maybe you've seen these examples. These are fish that fish. So it has a bioluminescent, a light up lure, and it waits for prey to come. And these may be what you picture, but these are by no means monsters of the deep. What you may not know is that these animals are adorably small. So this scale bar is about 2 inches. That anglerfish could fit in the palm of your hand. They're very small organisms, so they're not out to get us or anything, but they do form really important parts of the ocean community because they actually serve as a lot of really important food sources for things like tuna and other commercial fish. So it's really important for us to understand life in this twilight zone habitat. And one of the really incredible adaptations that we see in this twilight zone is called bioluminescence. So the ability of light, of biology, of life to light up. And one fish that can do this is called a dragonfish. And you are going to see this dragonfish that's been collected by a submersible making its own bioluminescent light. So these are able to light up. Bioluminescence is incredible to us, but it's actually very common in the ocean. About 70% of animals that live in the deep ocean can light up or can make their own bioluminescent light. And one of the ways that this fish uses this bioluminescence is for communication. So an alarm signal like you're seeing here, but it actually also uses bioluminescence to hide because some of these fishes can match the exact amount of light that's coming down from the surface with these light up pores on their belly to hide completely. So they're able to disappear. And some of them are even able to produce a bioluminescent sniper scope. So many organisms in the deep ocean cannot see in red. Red light doesn't travel very well in water. This is why when you're snorkeling or swimming, the water around you looks blue. The red light is lost very quickly. And so most organisms have actually lost the ability to see red light. But this fish has gotten around this and makes its own red light. It can see red light, and it uses essentially night vision goggles because it's able to see this red light it's producing and its prey cannot. So really incredible adaptation. It's also able to swing its whole face open. So here you get to see the hand for scale. And when these fishes were first collected, this is called a loose-jaw dragonfish, people thought it had been damaged because how could you not have skin around the throat? But it turns out that this is actually the true morphology of the fish. It does not have skin there. And this helps the fish to shut its mouth very quickly. You can think how hard it would be to push all that water with a big skin flap. Instead, it's just evolved to just not have skin on the throat. So pretty incredible habitat adaptation there. So we're going to take a little deep sea tour today and check out a few different habitats. And one that I'd like to highlight that you may be less familiar with are actually cold water coral gardens. So some of us may have had the privilege to visit a coral reef in shallow water. We know these are really beautiful habitats that support diverse ecosystems. There are also corals that live in the deep ocean to very deep depths. So this is at 6,000 feet out in the Pacific Ocean. And you see here a beautiful garden, in my opinion, of corals that are actually feeding on small plankton in the water. So corals in shallow waters actually have algae growing inside their tissues that helps them to get food through photosynthesis. So really incredible adaptation. These deep water corals don't have those algae. Instead, they're actually feeding in the water. And they grow really slowly. So at one time, some of these corals, like this Metallogorgia gold coral that you see here, whose skeleton truly is gold, these species were harvested for things like jewelry, but we later found out that they can actually grow for a really long time and be more than 1,000 years old. So these are extremely long-lived and slow-growing and very vulnerable ecosystems. And they create really important habitat in the deep ocean. So you may be able to see that on this coral, there is a crab. This species of coral is always seen with that species of crab. They have this very close association, and the crab is able to get high up into the water to get some food, gets a bit of protection from the coral, and the coral potentially gets cleaned by the presence of the crab. And so we see some really incredible associations. This is that crab up close. The corals also form important food sources for organisms like this sea star. Anybody know how a sea star feeds? So instead of going to, maybe we shouldn't make the human analogy, because the sea star feeds by actually averting its whole stomach, spitting out its stomach into the environment, digesting material, and then sucking that stomach back up. So it would be very rude to do this at the pizza shop. So really incredible adaptations that we're able to see to feed on some of these deep water corals. And so hopefully we're starting to get a picture that the deep ocean is made up of really diverse habitats. And one of the things that we study in my research team is how those conditions in the deep sea influence who lives where. So students in my lab at SUNY Geneseo and in my marine biology class at the college have done a lot of work conducting their own research project. In this case, actually identifying and counting fishes in the deep sea. So they've combed through many, many hours of deep sea video and figured out which fish live at which depths. And they've counted and identified more than 1,137 fishes. So they've been working very hard. What they see are these really distinct changes in the fish community as you get deeper. So in what I'll call the somewhat shallow deep sea, it's not that shallow, but down to about 3,000 meters or about, about 1,000 meters or 3,000 feet, we see fishes that look like fishes, maybe more like you might be familiar with. They have a forked tail, a forked caudal fin. They have some color to them. But as you get deeper and deeper, we end up with very different looking body forms. So we see fishes like this one. This is a type of goosefish that is not very good at swimming. It's very good at sitting on the seafloor and waiting for prey to come to it. And we see a really extreme example of this in a fish called the tripod fish, which is called the tripod fish because it stands like this and waits for prey to come to it. So it's sending these spindly fin rays out into the water and waiting on prey. And as you go even deeper to depths of about 3,000 to 19,000 feet, we start to see even more different body forms. So fishes start to look very brown, they start to look very elongate, and a lot of them are sitting and waiting on the seafloor or are eel-like fishes that swim very slow. And so what the students have found in this project is that the community of fish that you see depends on things like the temperature of the water. It's getting increasingly cold as you go down to those deep depths. Depends on the pressure. So pressure is also getting higher with increasing depth. The amount of light that is available to a fish, and even things like the amount of oxygen in the habitat. So all of these are influencing which fish live where. But I'd like to take us also to the deep end of the ocean today, one of my favorite habitats. So does anybody know how deep the ocean is on average? Whisper to your neighbor.
1,000 feet.
1,000 feet. Anybody beat 1,000? 1,000 feet. 1,001. Deeper than 1,001. Yeah.
Never go first.
Deeper than 5,000. 50, okay, shallower than 50, deeper than 5. So about 12,000. About 12,000 for the average depth feet. So super deep. So, and actually about half of our planet is at that really deep depth. But the oceans actually extend even deeper than that, all the way to 11,000 meters or 36,000 feet. How many have been in a plane before? Some of us? Yeah, so that's a common cruising altitude for commercial aircraft, is 36,000 feet. And so if you picture looking out the window and how far down it is, that's how far down it is to these deepest ocean sites in some of these trenches. And so I'm really excited about organisms that live in the hadal zone. These are deep sea trenches. You may recognize the word hadal from the Greek underworld, Hades. This is the bottom of the ocean. And these hadal trenches are deeper than Mount Everest is tall by some distance. And they're found around the world, mostly around the Ring of Fire. You may have heard of the Mariana Trench, which has Challenger Deep, the ocean's deepest depth at 36,000 feet. There's also places like the Kermadec Trench, Peru-Chile Trench, and a ring of them all the way around the Pacific. And so in my research, I have the opportunity to go explore some of these deep sea trenches, figure out who lives there, and then understand how they're surviving in a habitat that we think of as really extreme. And what I hope you're wondering is, how do you get there? How do you study some of these sites? It turns out it's quite difficult, because if you need to reach a site that is 36,000 feet away, you start to need something like 7 miles of cable to drag a net or a camera. And when you have a 7-mile wire, it can actually snap under its own weight. So we have to use other tools mostly to study these sites. And so instead we use what are called free vehicle landers. So landers like in space exploration. And these are not connected to the ship. So they have a weight on them. We deploy them over the side of the ship. They sink down. It takes several hours for them to sink to the bottom. And then they'll record information like some of the video that you're going to see, or they'll collect things like mud or water or organisms that we'll use to study. And then they actually have an acoustic signal, or they have an acoustic release that we can call from the ship. It sounds a little bit like a dolphin. If you have a great dolphin impression, now is your moment. No one ever takes me up on this, but someday someone next time. Yeah, next time. So it sounds like a dolphin, and it actually tells the lander to drop the steel weight that it's used to sink down to the bottom, and then positive buoyancy from these glass spheres will actually bring it back up to the surface. And then we all go to the top of the ship and we look for an orange flag in the water. We drive the ship over and we collect our gear and get whatever information that vehicle got. And so this includes cameras, including some of the video that you're going to see next, as well as structures like this fish trap here that we use to collect fish from these deepest ocean depths. And so to us, these hadal conditions in the deepest oceans are very harsh. There's high pressure, there's low temperatures, now closer to 32.5 degrees Fahrenheit, and they're relying on food that sinks down from the surface. But a trench is like a big funnel. So it's this big underwater valley, and we think that they're actually collecting more food than other spots in the deep ocean. So we actually think that trenches are able to give us an even more abundant community than in some other parts of the deep sea. So I'm especially interested in fishes and fish adaptation. To remind you, this is what some of our fishes look like that were living in those sites just before the trenches. So some of our abyssal fishes from about 13,000 to 19,000 feet deep. They're often long eel-like fishes that are found in solitary numbers. And this is what many deep sea fishes look like. But when you cross over into a trench, you're left with some really different fishes. So this is my favorite animal in the whole world. They're called hadal snailfishes, and they're in a group called the leporids. And one of the things that I love about them is that these fishes look quite fragile. So they're small. They're about this long, a couple of 6 inches long. They're pink. If you look at them, you can actually see through their skin. That is the liver of the fish that you can see even in life. And something that looks so fragile and really is so fragile is actually the deepest living fish in the whole ocean. So these have been able to survive in a habitat that we think of as very harsh, but to them, this is their home. And in 2017, we had the privilege to name and describe and discover this deepest living fish that lives to depths of greater than 8,000 meters, so more than 20,000 feet, quite a long way down. And we call it the Mariana snailfish. And it is among some of the deepest living fishes that have ever been described. And I do a lot of work on its physiology, on its ecology, but one of the things I wanted to share with you today is how it eats, because I thought that this is a fun story. So hadal snailfishes eat small crustaceans like this one. This is called an amphipod. You can think of it as a relative of a roly-poly that you might find in the garden. These amphipod crustaceans are very abundant in the deep ocean, and hadal snailfishes are really good at eating them. I pulled more than 5,000 amphipods out of the stomachs of some of these hadal snailfishes. And one of the ways that they do this is actually through a really interesting adaptation where they have a second set of jaws in the back of their throat. So you may see in this video of the fish feeding, to us it kind of looks like it's choking on the prey. But it's not. It's actually chewing that prey with a second set of jaws that are in the back of its throat. So this is a CT scan that we've taken of this fish, similar to what you'd have done at the hospital. We use it to study fish morphology. And here you can see this very strong jaw in the throat of the fish. And I actually have a 3D printed version of this that I'll pass around. And you can maybe appreciate that if you were eating these little crustaceans that are so good at eating other soft tissue, you would definitely want to be able to crush them up before they ended up in your stomach. So I'll pass this around here and then I'll hold it up to people on Zoom. Yeah, okay. You can see. So a lot of fishes have these second jaws, but in the snailfishes in this hadal group, they're very robust, and we think that helps them to live in these deep sea habitats. And so some students who work in my lab are continuing with some of these projects, looking to understand how the skull shape of a fish can tell us about how it's adapted to feed in its environment. So we'll be happy to share more about that if you have the chance to come to Great Day on campus later in the semester. And when we go to these deep sea sites, there's always more to discover. So we're often seeing organisms that we've seen before, but almost every time we also see something completely new. So this was a really amazing story from an expedition to the Mariana Trench, where we put down this camera to actually monitor this equipment. So this equipment goes down and collects mud, and this camera that was just supposed to monitor that tube going into the mud actually saw something that no one had ever seen before. This really beautiful fish. It is another type of snailfish that lives in these deep sea trenches, and we call it the ethereal snailfish. It's never been collected. It doesn't have a scientific name. And so if you are interested, for example, in getting involved in deep sea exploration, there's a lot more out there to discover and a lot more beauty out there on the planet. I wanted to share with you a recent story from an expedition working with some submersibles. Often we're sending cameras and traps down and not going to the deep sea, but occasionally we get the privilege to actually go to these beautiful habitats ourselves. And we did in 2022 have the opportunity to work with a submersible called Alvin, which is America's premier deep sea submarine. It's completed more than 5,000 dives and contributed to countless scientific discoveries. And in 2022, we went out and we had the opportunity to test the new vehicle for science operations that can now reach 98% of the global ocean. So really exciting. And I'd like for you to look at this submersible being deployed and see if you can spot my favorite piece of equipment on this ship. And two, I'd like you to look at the water. So first, my favorite piece of equipment will come up in a moment. It is this rope. So the submersible is lowered over the side of the ship, and there is an incredible rope that is able to lift the 40,000-pound submersible and safely take it into the water and then bring it back up. But what do you see in the water? There's a lot of stuff out there.
Yeah,
It is a seaweed. Anybody know the name of this one?
It's sargassum.
It is sargassum, yeah. And so if you've had the pleasure to be in this area, you may have seen sargassum algae. It's really incredible. It spends its whole life floating at the surface. And we often think about it as a surface organism because it's an algae. It needs the sun to be able to grow. And sargassum abundances are changing with climate change, causing major socioeconomic and environmental impacts. And so here we're looking at sargassum abundances. They've increased greatly in the past few years, and it's also washing up on beaches. So we're seeing a lot of sargassum showing up. And there's even a desire to sink some of this sargassum to try and trap carbon in the deep ocean. But we don't really know where that algae is going to go, what will happen to it. And so if we want to seek solutions like that, we need to understand what happens to that sunken algae. And it does actually end up on the seafloor. So on this expedition, we saw a lot of sargassum on the seafloor. And one of the students who works with me at SUNY Geneseo, Avisaj Sekurore, actually counted a bunch of this sargassum and identified piles and piles of it on the seafloor. So there's a lot of it. And it doesn't just sit there. It gets used by an animal that I think is truly incredible and that I hope you will enjoy seeing here. So this is my Act 3. This is, anybody want to guess what it is? Let's play this game.
The tripod.
I was gonna say it's got the telescope for the tripod.
Cool. So we're identifying these common features of spindles to help sense. It is in a different group than the tripod fish. It is actually also a crustacean. So like a relative of a lobster or a crab, this one is called an isopod. And this animal is swimming backwards and upside down. So the antennae that you're looking at are coming off the head. It is holding the sargassum in its mouth, and it is using a 4-paddled upside down backstroke to carry this algae. So we got to meet this animal several times across this expedition and across a really wide geographic range. And we also thought it was incredible. And so we wanted to know, is it eating this sargassum? Is it eating other things? How is it adapted to feed on algae when it never sees the sun? So it lives very, very deep in the water. And so we did collect some of these organisms carrying algae, and we were able to, there's a nice little flyby of one. We were able to look very closely at their gut content to understand what they were eating, at their mouth parts to understand how they're eating. And we found that they're very, very good at eating this sunken algae. It's an extremely important part of their diet, the most important part as far as we can tell. And they have these very well-adapted serrated teeth to be able to eat the algae. And they actually have a symbiotic gut microbiome, just like we do, that helps them digest. But their gut microbiome helps them to digest that algae and get nutrients. So this animal, although it lives miles below the surface, is closely connected to what's happening at the surface and impacted by things like changing algae abundance with climate change. And so we have a tendency to think of the deep oceans as being something other, something otherworldly, something alien, but they're very closely connected with the rest of the ocean. And I think that this animal gives us a really beautiful illustration of that. Along those lines, our actions at the surface do show up in the deep ocean. So here you're seeing 3 images. 2 of these images are sponges, and one of these images is sargassum that can. And unfortunately, trash is not uncommon in the deep ocean. So when we go out and we explore these sites, we're regularly seeing instances of trash and debris that shows up in the deep ocean. This is a glass bottle that a fish has found its way into. And these are really common observations in the deep sea. So some of my research team in my lab have been looking and counting and identifying trash in the deep oceans. And unfortunately, I've found quite a lot of it. So you can actually see all sorts of cans, Spam cans, soda cans as well. They found fishing gear. This is a bike tire. There's a lot of trash that's ending up in these deep sea habitats. And we've published on this late last year with the help of collaborators at NOAA who helped us identify and document how closely impacted the deep oceans are by surface activities. So although the deep sea may be out of sight and out of mind, it is part of the ocean and is very closely connected to what we do at the surface. If you are excited to learn more about the deep sea or you want to get involved with protecting deep ocean ecosystems, I recommend checking out this website. This is the Deep Ocean Stewardship Initiative. They have a lot of great material, including deep sea art, as well as information about how things like climate change impact the deep ocean, how things like deep sea mining would impact the deep ocean. And so please check out those resources there. But what I'd like to leave you with this evening is that deep sea habitats are worth protecting. So one habitat that we didn't have the opportunity to explore yet are hydrothermal vents. So I mentioned that most deep sea habitats are relying on food that falls from the surface and not relying on making their own food. This is an exception. So at these active geological sites, these hydrothermal vent sites, warm fluid boils up out of the earth and comes out. And with that fluid, it has really special chemistry, including things like sulfur, that organisms can actually use to get energy. So we're used to most life energy coming from the sun, but this process, which is called chemosynthesis, can make energy and organic material available without sunlight at all. And this absolutely transformed our understanding of biology when it was discovered with the help of the Alvin submersible in the 70s. And we see that not only are these habitats incredible biologically, they provide really valuable opportunities to get new inspiration for medicines and compounds. There's compounds and enzymes that work in these really hot vent fluid that are used now for anytime we need to replicate DNA in the lab. So this material is really valuable, and the person who took this video also described it as a cathedral. So these are incredible habitats. This structure that you're looking at is called BB Woods. It's the deepest hydrothermal vent. It is hundreds of feet tall, and it is an area unlike any other. So these are spaces that are worthy of as much respect as our national parks, as these other spaces that we treasure so dear. So with that, I would like to thank the very many people involved in just some of the science that you saw here today, including a really fantastic lab team. I had the pleasure to work with more than 40 SUNY Geneseo students in my lab just in a short time. I'm grateful to all of them, including those also in the marine biology classes. And a big thank you to the ship's captains and crews and scientific parties that helped collect this material. No one achieves anything alone, especially deep sea biology. And I'd also like to thank the National Science Foundation, who has been instrumental in providing funding for this work, in addition to the other fantastic work they support, including other valuable things that we use all the time, like the invention of that 3D printing, the invention of the internet, American Sign Language, Doppler radar, MRI technology, Duolingo, LASIK eye surgery, and finding matching transplants for kidney patients. So thank you to the National Science Foundation. Thank you also to SUNY Geneseo, and thank you very much for your time. So I will leave you with this beauty, but I'll open the floor to any questions that you have. Thank you. I can see questions in the chat too, if those come in. Well, thank you.
So one question that comes to mind, you kind of, when you show that comparison of the sargassum increasing over, I forget it was 2009 to 2018, is that what it was?
2011.
So, okay, 11, so 7 years. Are we able to observe at locations to see if we're seeing population change
In these
of these species? Or?
It's a great question. We don't know yet. So that isopod was seen twice before ever. Once on the 1948 Swedish deep sea expedition when it was originally described, and then once on by a lander in 2013. So those 32 individuals are what we've seen. But given the importance of sargassum to the diet and the fact that other deep sea animals are using that algae as a food source, it's very, very likely that deep sea ecosystems are impacted by changing abundances. And we know that climate change does impact the deep ocean in other ways, including things like changing oxygen concentration as well.
Right. Is there a negative to it?
Yes,
That
yeah.
That we've observed?
Yes, climate change is negatively impacting deep ocean ecosystems, especially with the oxygen. So cold water actually holds more oxygen. So as the oceans warm up, a lot of habitats are losing oxygen, and that's the major impacts, although there are others as well.
How do you come up with identify the name of Fidget?
How do we identify the name? Thank you so much for asking. It's a great question. A good taxonomic name often tells something about the organism, helps you identify it. So usually when we name species, we try to come up with something distinctive about it. We also try to honor the location that it comes from. And sometimes they're used to honor people in the scientific community or others. For this particular species of the deepest living fish, we named it as a thank you to the crews who work on oceanographic research vessels. So we named it after one crew member, but in honor of the people that run the ships, that keep everybody fed, that keep the ship from running, or that keep the ship running as well. Yes, thank you.
In like the beginning, what was that like fish that was like really long? Like when we walked in, that like kind of like.
I think you might be referring to the gulper eel that has a very big face and a really long body. Maybe I can play the video at the beginning too. If it's the one I'm thinking of, it can actually inflate its whole mouth when it's stressed, which I guess we can do too, but it does it in a really incredible way because its mouth is half as long as its body. So for these organisms that live in the deep ocean, you don't know when your meal is going to come next. And so a lot of them are adapted to eat anything they meet. Some of these fishes can actually eat meals that are basically as large as themselves, including that gulper eel that can unhinge its jaw. Yes, thank you.
The fish in the Haydale region have eyes, but do they function similar to the fish at much shallower depths, or are they completely different?
This is an excellent question. We don't know yet. So we have collected eye material from the fishes to try and figure out this question of can they see? They don't respond to the light from the camera in the same way that some of these other fishes do. So when we drive a remotely operated vehicle, an underwater robot up to some of these fishes, they respond to the light, and those Hadal ones don't. They may be able to sense very low levels of light, we don't yet know. Bioluminescence is way more common than it's ever really considered to be. But the trick with trying to see is there any light in the hadal zone is that to film bioluminescence, you have to turn your lights off. So you have this trade-off of you can see the light that the organisms are producing, or you can see the organism. And we're at the see the organism spot of hadal science, but I'm excited for people to look at bioluminescence of these depths. Thank you. Yes. Fish.
What were those ones that like could extend their body?
The gopher eels. Actually, a lot of these can extend their body. So these anglerfish on the right, they also have expandable stomachs. And in some cases, they've been seen, they're basically a mouth and a stomach with a tiny little tail. They've been seen with prey items in that stomach that are very, very large. So it would be like if you could unhinge your jaw and eat a whole pizza. Yeah.
Like the one that's mouth that goes like that and then.
I'm gonna pull it, but it's called a gulper eel. So please look up videos of your favorite sea organisms. I'll keep that playing again while we chat. Yeah.
When you bring the fish or
That's one.
things up from the really, really deep depths and you bring them up to the ship, because it's a different temperature and a different what pressure, thank you. Do they survive or do they die on the way up or when you get up there or?
Most of them do not survive the journey up. One of my favorite old ideas in really old papers, it's called the expansion hypothesis. And the idea was that if you brought up a fish from 20,000 feet, that at the surface, it would be very, very big because it was so compressed down there. And that doesn't happen because these fish and those organisms are mostly made of water, which isn't very compressible. So they don't survive the trip up because their cell envelopes, their proteins are not working under that really light pressure now, but they don't explode or expand. They look as they do in life, essentially.
We can study them.
We can study them, and we do get a lot of information from some of these collections. So there's been cases where we've, for example, collected 2 isopods and been able to tell a lot of information about who it is, what it's eating, and now those organisms are in museums for future work as well. So. Oh, the polychaete we liked. So the elongate swimming, the beautiful one that might show up again, is called a polychaete. It is actually a relative of an earthworm in a group called the annelids. And I love that example because we maybe don't appreciate the worms enough. They're very diverse and very beautiful. And that swimming worm that you see is extremely good at swimming. Some of those species are also predatory, so they're very fast and able to hunt. And they have really high diversity in the deep ocean. And you can go study them if you want. Dr. Bosch.
You mentioned the deep sea that we should care for and protect it like we do our national parks. But who really, they're mostly in international waters, so who really has jurisdiction over what goes on out there?
It's very important to ask. In many cases, speaking about the seafloor specifically, the International Seabed Authority and international treaties govern what can and can't be done in those waters. And how many of us have heard of the International Law of the Sea Treaty or the International Seabed Authority? Maybe not very many of us. So it is worth paying attention to not only protection within our own borders, but also what's happening in these shared waters, because not only does that body have to be able to set policy, it also has to be enforceable, or that everybody has to agree that they're going to abide by that international authority or that international law.
Can you go back to that one that's like the mouth opens?
Let's see, there's your polychaete.
It's not on this part.
It's not on this part. Okay, can you tell me where it is? There's a lot of cool jaws in the deep ocean. This one. This one. Yeah.
Yeah.
This is a loose jaw dragonfish. Yeah.
Yeah, can you like, what happens when you like bring them to the surface? Do they survive?
Some of these do. So some of the ones that live in that twilight zone, they're not as deep as some of the others. The pressure change, the temperature change is not as much. And so there are some people that have actually been able to keep species like this in aquarium and study them.
Guess what he wants now?
Yeah.
I was just about to say,
There's a
you
good
keep
deal
these like
for
as
you.
pets. That was my next one.
It is only a matter of cost. So, yeah, to keep them. They're happier at depth.
And it looks like there's like teeth in the back of the throat at the
Yes.
top of it.
Yeah.
Like what are those?
That's another example, good eye. That's another example of the throat jaw. It's called a pharyngeal jaw. You may have heard of like a pharynx, a throat, called a pharyngeal jaw in fishes. And they're pretty cool. And there's one maybe being passed around. Yes, hello.
And the front jaw is more for just guiding food in, and then the pharyngeal jaws actually chew it up.
This is a great question, and it's not worth, or we shouldn't take it for granted, because some of these things are best guess from looking at the shape of the fish, because we haven't been able to see them feed in life. The best guess is that the front teeth act sort of like a cage, and then the back teeth do the processing. Most fish actually don't have tongues. So where we do a lot of our manipulation of the food, a lot of important moving around the food with the tongue, a lot of fishes need to use this second set of jaws because they don't have. One of them has a parasite as a tongue, an isopod parasite. Something to look up.
You just tell us what the name of this one is one more time.
Yes, the loose jaw dragonfish.
We're gonna
You
remember that.
can email me too and say, what was that fish?
Okay.
Take all your deep sea questions. Yeah.
What I was curious, what's the lifespan of some of these organisms on the bottom of the ocean?
A lot of them we don't know. A lot of them are very long-lived. So many organisms in the deep ocean are living in a cold habitat. They're living in a habitat that doesn't have a lot of food, and some of them can live for a really long time. So some of those coral species can live for 6,000 years, humbling longevity. But some of the fishes can also live for a long time. Does anybody know this fish? This is called a ruffy. Yeah, and so some of these species that are in a genus called Hoplostepus, some orange ruffy, can live to be 80 to 100 years old. And so, as you can imagine, that's very challenging for a fishery. Some of these are commercially fished, but it's very hard to have a sustainable harvest of a fish that is living as long or longer than we are. Yeah.
What's that on the table?
This one, great. This is a fish called a stargazer. It's a little bit shallower living, but it's one of my favorite 3D prints. I'd like you to tell me something about what you think this fish does or eats or where you would find it.
Is that the
You can
actual
look at
size of it?
It is 1/6 of that size.
Oh, this is 1/6 of this size. Okay.
Yeah, and you can take your time.
Like,
Where are the eyes pointing?
up.
Up, yeah?
So we can see lights.
Yeah.
And then it like probably like waits on the bottom, and then it looks up, and then when it sees it, it opens its mouth, and its mouth looks like it's like pointing up.
That's it, that's it. So
It
you
just
are,
looks like this pretend.
So you are now a functional morphologist, where you look at a structure, look at a skull, and you make hypotheses about what it feeds. And these are excellent hypotheses. They happen to be true, but they're excellent because you have a reasoning and they're testable. So you are a scientist. Thank you for sharing.
Good job.
You would explore trenches in like the Atlantic versus the Pacific.
I'd like to see it
Do
as
you
well.
find the same species or are they discrete ecosystems?
They are mostly discrete ecosystems, and it turns out that they are mostly discrete ecosystems even in the Pacific. So there are little islands of, inverted islands of biodiversity. Some of the Atlantic has far fewer trench habitats. So there's the Puerto Rico Trench, the Cayman Trough, and then the South Sandwich Trench in the Antarctic. The Puerto Rico Trench is really different than some of the Pacific trenches. It's home mostly to these fishes that are called cusk eels, another favorite, and doesn't have snailfishes in it, for example. So there are differences between these trenches, and we think that may reflect the evolution of the species into these habitats, as well as some barriers between some of the trenches. No, it's cold and late. I am happy to answer questions over email. Thank you very much for your time. And there's another exciting talk coming up soon.
First of all, thank you so much for coming tonight and sharing your
Great
knowledge
job.
about oceans. In a small way for us to show our appreciation, we'd like to give you a
Thank you.
certificate for sharing your knowledge about deep sea oceans with us.
Thank you. That's very sweet of you. Thank you very much.